All right, welcome back, everybody. We're doing another deep dive today, and this time we're taking a closer look at acids and bases.
Uh-huh.
We've got this really cool excerpt from Understanding Acids and Bases that we'll be referencing, and it promises to be a fascinating look into these essential chemical substances.
It really does.
So when we think about acids, I think most of us immediately jump to that sour taste.
Yeah, exactly.
Lemons, vinegar, those kind of things.
Right.
But what's really happening at the molecular level? What makes these substances so sour?
Well, at their core, acids are substances that are very generous.
Generous?
Yeah, you could say that. They're generous with their protons, tiny little hydrogen ions.
Oh, interesting. You mean those H+ ions?
That's right. They love to donate these protons, share them around, and that's what actually gives them their acidic properties.
So it's like they're little proton philanthropists.
Kind of. A classic example is hydrochloric acid, or HCl.
Ah, yes, the stuff in our stomachs.
Exactly. It's crucial for digestion, and when it breaks down, it splits into a positive hydrogen ion, that H+, and a negative chloride ion, Cl.
So that's a prime example of proton donation in action.
Absolutely.
But I'm guessing it's not always that simple, right?
You're right. There are different ways acids can be, well, acidic.
Okay, I'm intrigued.
Take boron trifluoride, BF3, for instance.
BF3.
This one doesn't actually have a hydrogen to give away.
Huh. So how can it be an acid then?
Well, it gets a bit more complex here.
All right, lay it on me.
BF3 acts as an acid by accepting an electron pair instead.
So instead of giving away a positive charge, it's attracting a negative one.
Exactly. It's a different kind of sharing, but it still achieves that acidic behavior.
Fascinating stuff. So acidity isn't just about giving away protons, it's about attracting negative charge overall.
You got it.
And I guess that brings us to bases, the other side of the coin.
Right.
And we all know that slippery feeling, like soap, for example.
Yeah, soap's a classic
Yeah,
base.
and baking soda, too, right? It has that slightly bitter taste.
You got it. Many bases do have that kind of bitterness to them.
So what makes bases so slippery? Is it just a random property?
Not at all. Remember how acids donate those protons?
H+ ions, yes.
Well, bases are the opposite. They love to accept those protons or even donate electron pairs.
So it's a kind of proton tug of war.
In a way, yeah, they're balancing each other out.
Interesting.
And that proton exchange is what gives bases that slippery feeling.
I wouldn't have guessed that those two were connected.